Hello, this is our third video in the differential equations lecture series, and in this video we're going to actually start solving some of the simpler differential equations. In particular, we're going to move towards separable equations, and we're going to start to talk about differential equations and integrals as antiderivatives or derivatives as anti-integrals. So let's go ahead and get started with that. So this is our third lecture. So we'll put this here. So what do I mean by antiderivatives? Well, let's take, for example, a very simple kind of differential equation. For example, let's say dy dx equals, well, we could just call this, for example, f of x. All right. So, what do I mean by antiderivative? Well, integrals and derivatives basically undo one another. So, the new thing we'll learn here is that basically, if these two things, remember, this is the derivative of y, but this is also some function, right? So we could call this derivative something like g of x, right? And if g of x is truly equal to f of x, right? That means, for example, this is g of x, right? And if g of x, this arbitrary function, equals f of x, then they have to be the same. The new trick we're going to be able to do is not just algebraic manipulation, but if these truly are the same function, then the integral of g of x dx has to be equal to the integral of f of x dx. Because they both refer to the area under the same functional curve, and if it is the function, then the area under the function has to be the same. So you can start to see how this is going to be an antiderivative. So for example, if we do this in the simple case, and let's just make it x. So let's say dy dx equals x. Well, I can integrate both sides. I can just do the integral of dx of this function has to be the integral of dx of this function. This side is pretty easy. This integral is just x squared over 2 plus a constant. But what about this side? This is where this idea that integrals and derivatives are basically undo one another. I'm going to integrate the derivative. And integrating the derivative just does and undoes the same function. It's like taking the inverse of itself. So this is just going to be basically the integral of dy. Notice this looks something like treating dx and dy as fractions. This is often used like shorthand, but just be aware this is what we're actually doing. We're actually integrating both sides, dx. And of course, the integral of dy just equals y. So in this case, our answer is y equals x squared over 2 plus c. We can always double check this by putting it back in our equation. Remember, our equation was y prime equals x. So if we put this function back in and take the derivative, we get the derivative of x squared over 2, right? Bring it down. This is just x. The derivative of a constant is nothing. So y prime equals x. And very good. We got a check mark. So this is basically the new form that we're going to learn today. So we have still all our algebraic tricks, but our new trick is that if two functions truly are equal to one another, we should be able to take this derivative of both functions and they should be equal to each other, right? The integral of both functions, right? Because the integral is just the area under the curve. So that's basically our new trick. And we've seen that works there. Let's move this out of the way. All right. So let's do a few examples of this. Right? And we've done some of these before and guessed what they are. We'll just do a few more. All right? So we have y prime equals x, but what if y prime equaled y, right? Now what would we do? Well, this is like saying dy dx equals y, and we can still do the same thing. We can integrate both sides over dx, integration of dx. But notice that this doesn't help us that much, right? This is not really good because y is this thing that I want, right? And I'm integrating with respect to dx, so y is already a function of x, but I don't know how to do this. But our algebraic tricks still hold. So before I do the integration, I can also just say dy dx, remember, equals y. That's from here. But I can still, right, we have our new integration trick, but I can still use all my old algebraic tricks. So I can say 1 over y dy dx equals 1. This is just moving this y, dividing both sides by y. And our new trick is integrating both sides. And I'm going to do that integration dx. And this just makes the integral over dy, this dx. So this is the integral of 1 over y equals the integral dx. This just is the natural log of y equals x, right? Don't forget, we need this constant here. Remember, derivatives and integrals undo one another, that's true, but in the process of doing and undoing it, you lose information, right? Because if you have something like x squared, let's say plus 2x plus 3, what happens when I take the derivative? I get 2x plus 2, right? And this 3 goes away because the derivative of a constant is a constant. What happens when I take the integral? I get x squared plus 2x, but I have to realize that I lost this 3. And that's where I put in this constant, right? And this constant is going to be defined by and determined by some kind of, we call them initial conditions, but basically we need one plot point on the graph. And let's go ahead and work that out here and we'll see what that's going to be. So if this is our solution, then now we can go back to doing algebra, right? I can take e to both sides. E to the ln of y is just y times e to the x plus c. E to the x plus c is just e to the x, e to the c. This is just, I'll call this thing, right? E is just a number, c is just a number, so I'll call it d, e to the x, where d is our new constant. For example, if, y of x equals 0 equals 1, then I can solve for d. For example, here I would say y of x equals 0 equals 1 equals d, e to the 0 equals d, d equals 1. All right? And in that case, y would just equal e to the x. Let's go ahead and see and make sure that our new tricks worked. Remember, we just did an algebraic step and divided both sides by y, and then our new trick of integrating both sides. If we plug this in, we should get y prime, and what's y prime? Well, the derivative of e to the x is e to the x, and that, of course, equals y. So indeed, it fulfills our differential equation. Okay? So we can see we can use this new form when we have y's, right, on one side, when we have x's on one side, but we can also go the next step further in abstraction, and let's think a little bit about what are called separable equations. As long as I can write my equation something like y prime equals some function of x times some function of y, and I'm just calling it f and g to keep it separate. As long as I can do this, then I can solve things in this very simple way, right? How would I solve this? Well, this is just dy dx. I would just move this over and say 1 over gy, I'm just dividing both sides by this, equals f of x. And then I can integrate and say 1 over gy dy equals the integral of f of x dx, right? So I've separated the differential equation into two integrals that I should be able to do rather easily. All right, so this is the whole key. Basically, this whole move is how we deal with separable differential equations. And this course in this video series is basically built in a way that we're going to go through how to solve differential equations from some of the easiest techniques to more and more difficult. So a way you can think of it is basically a checklist. So the first thing on our checklist now is to check, is it separable? So separable. That is, can I write it in this form? If I can write it in that form, then I should solve it in this way because it's very quick and very straightforward. If it's not separable, if it's not a first order separable differential equation, then I can't use this technique and I'll have to move to a more difficult technique. But this should always be an early on check to make sure you can't use this, to see if you can or can't use this very simple tool in your toolbox now. All right, so for example, let's do a couple of these differential equations to give you some examples of where we're at. An equation where we could start is, let's say we have y prime equals xy over y squared plus 1. All right, so is this separable? Yes, it's separable because I can write this like x times y over y squared plus 1. Now that I know it's separable, I'm going to use our technique here. So that is to say that y squared plus 1 over y dy equals x dx. Right, so I'm just flipping, I'm moving this g of y over, right, inverting it and integrating both sides. Notice that the sum of integrals is the integral of the sums. So this is the integral of y plus the integral of 1 over y equals the integral of x. And the integral of y here, this is just going to be y squared over 2 plus the natural log of y equals x squared over 2 plus c. All right. So that is a solution to our differential equation. This kind of solution actually adds a little bit new language to how we can describe differential equations. You notice that I don't just strictly have y of x, all right? So we can say we have several different solutions. So one solution to this equation would be, you could have guessed one solution is y equals 0. Right? So if y equals 0, this equals 0, and if y equals 0, the derivative equals 0. This is often called the trivial. This is called the trivial solution, right? So you can often find simple solutions, and it often happens when y equals 0 or x equals 0. There's often trivial solutions. There's also this kind of solution. This is called an implicit. So this is an implicit solution, this guy here. Because it tells us how y is related to x, but it doesn't explicitly, so it doesn't explicitly tell us y equals some function of x. That would be an explicit solution, right? So we have different ways now to name the solutions we have. We have trivial solutions, implicit solutions, and explicit solutions, right? So Oftentimes the very end game is to get an explicit solution, but sometimes implicit solutions are all right. And if someone just says, I want a solution, then you might be all right with the trivial solution. Okay. There's a couple other things we want to go over in the time we have remaining here. And that is, and this goes well with separable equations, and that is the inverse functional theorem of calculus. So let's inverse functional theorem. All right. So what do we mean by the inverse functional theorem? This comes in handy, and this is to say dy dx if the derivative of a function equals some function, and it can be of x and y, then dx dy equals 1 over that function of x and y. All right? So again, it looks a lot like dx dy acts like a fraction, right? I can flip it over like a fraction. Again, be careful. There's specific rules about when you can treat it like this, but in this case, you can treat it like this. We can give a simple example of this. For example, let's just say dy dx equals x, right? If we do this, we have the integral of dy equals the integral of x dx, or in other words, y equals x squared over 2 plus c. What if we use the inverse functional theorem? We say a dx dy equals x. And when we do this, 1 over x, right? We have to inverse both sides, right? So how would I solve this? Well, I solve it like separable, right? I'm going to multiply both sides by x. So I'll have x dx equals 1 dy. And of course, you see that I just switched the sides of this equation, right? So these two equations are equal and going to give me the same answer. All right? So this is a perfectly valid trick you can do. And so sometimes it helps when you have separable equations to recognize you can flip it over. Sometimes this is handy because maybe you don't want 1 over a function if it's going to be some kind of logarithm. Maybe you'd rather have it to the positive power or negative power. But this inverse functional theorem allows you to flip both the derivative over, right, and change it from dy, the change in y with respect to x equals a function, to the change in x with respect to y equals 1 over that function. All right? So this is another trick in our toolbox. So the two new tricks in our toolbox that we've learned is basically now that we can do this separation of variables, right? We can do the integration. If long as two functions are equal, the integration of those functions has to be equal. And now we can use the inverse functional theorem. All right. So we have a little bit of time left. So let's go ahead and look maybe at some examples of this in action. Right. So let's look at 3.5. Let me just pull up my notes so I make sure to do something reasonable here. All right. So whoops. Let's say, let me make sure I'm recording here. So, let's say we have dy dx equals 6y squared x. And let's even go for explicit solutions with a boundary value. So let's say y of 1 equals 1 over 25. All right. I'm taking this example directly from Paul's online notes on mathematics, so you can follow along there if you'd wish. They have some really great examples there to help you out. But let's look at what's going on. So what should I do here? Well, this is obviously separable. So because I can write it as a function of y times a function of x. So I can write this as 1 over y squared dy dx equals 6x. Remember that I can always integrate both sides with respect to x. And this is 1 over y squared dy equals 6x dx. Integrated on both sides. The integral of 1 over y squared is just minus 1 over y, or y to the minus 1 if you want to think about it that way, equals 6 times x squared over 2. And don't forget we need this c here. All right. Once we have this equation, now we can plug in our boundary value. So let's go ahead and plug this in. So when y equals, remember when I have this, this means y at x equals 1. Okay? So y equals 1 over 25. So this is minus 1 over 25 equals 3 times 1 squared. I'm simplifying. This is 3 equals c. Solving this for c gives me 25, 3, so 28. So this is going to be minus 28 for c. That means my solution is going to be minus 1 over y equals 3x squared minus 28, right? And remember, think back for a second, what do we call this kind of solution? We would call this kind of solution, remember we have the new words implicit and explicit. This might be called implicit, right? Because I don't directly have y, I have the reciprocal of y. So let's go ahead and flip this over. So now I have y of x equals 1 over 28 minus 3x squared, right? So this is my explicit. This is my explicit solution to this kind of problem, all right? So we played our variables, we played this, also played this trick. It's worth, since we have a couple minutes, still, it's worth thinking about one other thing when we think about these kinds of solutions, right? And that'll be where this solution is valid, all right? So we often call this an interval of where it's valid, okay? So when does this actually work? So if we look, oh, can we see it down here? Yeah, we can see it down there. This is not going to work well when we have a slope that's infinity, right? When we have a slope that's infinity, that basically looks like a straight line, so we'll never be able to escape that, right? So we want to look at this interval, excuse me. So we want to look at what's called the interval of validity in this case. So what's the interval of validity? Well, obviously 28 minus 3x squared cannot equal 0. If we have that equal 0, then the slope is going to, then this basically is going to explode, right? And if that can't equal 0, that means that x can't equal, let's see, 28 over 3 square root, and with a plus and minus, right? If it equals those values, then this is not going to work. This is going to explode. So what are the intervals of validity? And we can have multiple intervals of validity. So for example, as long as x is smaller than this number, then this works, right? Because now I'm back to this solution. As long as x is smaller than that number, right, then this is going to be a real number. And if that's a real number, that's fine. So for example, x, as long as x is greater than minus infinity, and it's less than minus 28 over 3 square root, this is fine, right? We can also have 28 over 3, 28 over 3. This is also perfectly fine because x is not hitting these edges, right? So this is perfectly fine. And we can also have 28 over 3 square root, as long as it's greater than that or less than infinity. So I actually have 3 intervals of validity, right? So it can't basically cross those barrier lines. In our case, we know where it's at due to our initial value, right? Remember, our initial value here was x equals 1, right? So if we had x equals minus 1,000, we would say it's in this interval of validity, right? If x equals 0 was our initial one, we'd say it's here. But in our case, we have x equals 1, so that means, that means our interval of validity is here, right? Because this number approximately equals plus or minus 3.05. All right. So our initial condition says that this is where the interval of validity is in our case. And we can get that, for example, by looking at the slope fields, which is something we will do in the next lecture. We can also get it by actually solving this equation. So if we look at our solution to this equation, right, we're actually going to get something that looks kind of like this in our case. And you can see from that solution that this are these numbers, right? This is 28 over 3 square root. This is minus 28 over 3 square root. And this is why we have intervals of validity. If we're in between these two numbers, there's no way we can escape. There's no way we can cross this boundary this way or cross this boundary this way. If we're over here for an initial condition, there's no way we can cross that boundary into this region. All right? So this is where the solution is valid, right? Outside there, it's basically never going to reach outside that interval of validity. All right. So let's look at our time here. We have a little bit of time. So let's maybe look at one more simple solution here to recall what we're working on. So, yeah. So let's say y prime equals x y to the third over 1 plus x squared square root. Again, this is separable. Let's also look at our interval of validity here. So let's give our initial condition. Y of x equals 0 equals minus 1. So first we separate this, and I'll skip some steps now that we're a little bit more used to this. So I'll just say 1 over y to the third dy equals x over 1 plus x squared square root dx. Interval. All right. This is fine. The solution here is minus 2y to the minus 2 has to equal 1 plus x squared square root plus c. Right? Don't forget our constant there. All right. This is just the definition of the integral of both sides. Now we apply our initial conditions, right? Remember, this is y of x equals 0 equals minus 1. So y equals minus 1, so minus 2 to the minus 1 to the minus 2 equals the square root of 1 plus x is 0, 0 squared plus c. When we do that, and so this is going to be minus 1/2 equals the square root of 1 plus c. So c equals 1 is going to equal minus 3/2. And therefore we can plug that back in to this equation. Remember, when I plug this back into this equation, we're going to call this an implicit solution. Once I have that implicit solution, then I can solve, right? So I'm just going to solve this guy by moving the 2 over, inverting it, taking the square root, right? And so I'll get the explicit solution of y of x equals plus or minus. It's going to be a plus or minus because I'm taking the square root of 3 minus 2, 1 plus x squared and 1. So this would be my explicit solution. All right. So if this is my explicit solution, what about my interval? So what's my interval of validity inside this guy? Well, in this case, we have a couple problems. We have x in the bottom of a fraction, so we still want to be careful that this thing doesn't explode in some way, right? Inside this fraction. Namely, if this thing goes to 0, that's not going to be good, right? But also, so we don't want 1 over 0. This is no good. And we also don't want the imaginary numbers. This is also no good for us. We want real slopes, right? If you continue taking math courses, you might come across a situation where the slope is imaginary and think a little bit about what that means. But in our case, we definitely don't want that to be true. All right. So in this case, we'll want to make sure both of these truths are true, and that'll give us basically our recurrence interval. So for our particular case, as we're running out of time, I'll leave this as an exercise for you. I'll give you the answer, and that answer is that our interval is going to be 5 over 2, square root of 5 over 2, x square root of 5 over 2. So this is going to be our interval of validity, right? So I encourage you to actually determine the interval of validity for this fraction with radicals and this given initial conditions, and think about and graph what the solution looks like, and make sure that, just like we had here, that the solution won't cross these boundary conditions. All right, so that's the end of the lecture for this time. For next time, we'll look at slope fields, and we'll also look at some shorthand to look at what families of solutions might look at. Right? Here but just to review a little bit of what we've done this time. So we've looked at the fact that integrals and derivatives undo one another. We lose some information, right? We note here that we lose constants each time we have this step, right? So if we do second derivatives, and we'll get to that later in the series, that will have more and more constants. We've also learned that we have separable, so that means we know how to solve equations that look like this, right? Namely, we just separate the y part, or the y function, from the x function and move those to the appropriate sides and do the integrals of both sides. We've learned that if two functions, f1, let's say f1 equals f2, if these two are truly equal, then the integrals of these two are truly equal. We've also learned the inverse functional theorem of calculus, and that's to say if this is true, then I can flip this over and say dx dy equals 1 over f of y g of x. And the final thing we've basically learned is we looked at the interval over which functions are allowed, right? So this is the interval of validity. So hopefully we've learned these 5 new tricks today. Thank you. We will see you next time.